This meeting is being recorded.
In the last video from chapter 19 on electrochemistry, we looked at the relationship between delta G and the equilibrium constant, KEQ. And these were all under standard conditions. So let's review some standard conditions requirements. That includes that our pressure is at 1 atmosphere, our concentrations are 1 molar, and we are at 25 degrees Celsius or 298 Kelvin. So a special type of this equation, when we have non-standard conditions, is this titled the Nernst equation, where to solve for our cell potential, we incorporate the E cell here under standard conditions, and then we account for any differences in concentration by solving for our reaction quotient. So this would be the same Q that we compared to the equilibrium constant K when we looked at thermodynamics in the last chapter. So if you recall, we would have to solve for Q, which is going to be some ratio of our products raised to any coefficient as an exponent over our concentration of reactants, also raised to any stoichiometric coefficient as an exponent. You will still continue to ignore anything that is in solid, liquid, or gas phase for this, because we know that our concentrations will not change. So only anything that is showing an aqueous concentration will be included. So this revised version, or this altered version of our concentration cell equation, or our delta G equation, now accounts for the fact that we're not in standard conditions. And to eliminate the natural log of Q, which we see up here in this version of the equation, we can plug in this number, 0.0592, over n, and that 0.0592 will incorporate all of these, the constant R, the gas constant 8.3145 joule per mole Kelvin. So that's eliminated or incorporated into this 0.0592. Faraday's constant, so remember that's the 96,485 coulombs per mole. That's incorporated, and then there's a number that kind of translates natural log to log. So all of these values are found in this magic number here, this 0.0592. We still have to divide by the n value, the moles of electrons that are transferred. So we'll do that in sample exercise 10 below. But for now, let's look at when we are at equilibrium under standard state conditions, our delta G value is going to be 0. When we have a spontaneous reaction, so we are going in the forward direction here, we're going to have a negative delta G. Our KEQ under equilibrium conditions will always be 1. Our K will always be much greater than 1 for a spontaneous reaction. And then let's relate our cell potential as well. So E cell at equilibrium will also be 0, as will delta G. And we'll see that this is positive for spontaneous reactions. So let's see what happens in sample exercise 10 here. We're asked to calculate the cell potential at 298 K. So we're under standard temperature, but we can see that we're under non-standard molarities here. So our concentration is non-standard. So as always, to solve for E cell, our cell potential, this is now going to incorporate this under standard conditions, and then we're going to add that in. So we're going to have E naught cell that we solve for first. We're going to use that. We're going to subtract 0.0592 over n times the log of Q. So we have to solve for Q, we have to find n, and we have to solve for E cell before we can plug in and solve for our E cell under non-standard conditions. So E cell, let's break this equation into half here. So we have our chromate ion will yield 2 chromium 3 plus, and then we have our other half reaction. Oh, actually, I'm actually going to include my hydrogens here as well. So I have H plus chromium gives me my 2 Cr plus and H2O as well, 7H2O. Okay, so my other half cell is going to be just what's left. So I have 6I negative, and that's going to yield 3I2. All right, so let's balance these. Let's make sure everything but charge is accounted for. So I have 2 chromium over here, 2 on this side. We're okay to move on. I have 6 iodine here, 6 iodine there. We are okay to move on to balance the charge. So what I need is the same amount of electrons going in as out. So let's see, I have plus 14 from the 14 hydrogens minus 2 here. So I have a plus 12 overall charge accounted for here. And then on this side, I have 2 times plus 3 or plus 6. So I'm going to need to add 6 electrons to the side to balance this out. So now I have 6 electrons plus Cr2O72 negative plus 14H plus will give me 2Cr3 plus 7H2O. All right, and now over here on this side, I have -6, I have 0, so I'm going to add the same amount, 6 electrons to this side, and now we're balanced with the charge. So now I know that this is going to be my oxidation reaction over here. We're losing electrons. Here we're regaining electrons, so that's my reduction half reaction. All right, so let's see how we can look up these values. So we go to our table to solve for our E cell, rather, overall, is going to be the E cat. So whatever our reduction value is here, minus our E anode. All right, so from the table, we would find that our E cat here is going to be 0.28 volts. Our E anode is, I apologize, I have the wrong values here. So our E cat for this equation is going to be 1.33. So again, this is for our chromium reduction, so 1.33, and then we're going to have minus iodine is going to be positive 0.54, so 1.33 minus 0.54. I get my E cell here under standard state equal to 0.79 volts. All right, so now I'm going to take that and I would plug that in here. First, let's solve for Q. Our Q is going to be our concentration of our product. So I have my chromium ion concentration squared, and that would be divided by both the chromate, Cr2O7, concentration. That does not have a coefficient, but I'm also going to plug in my H plus here, and that has a coefficient of 14. And then I also have my other product from the iodine here, I2, and we're going to cube that. All right, so let's leave ourselves some space here to plug in these values for our Q.
This meeting is being recorded.
Okay, so my Q now, I'm going to plug in the concentration of my chromium ion. So that was 1.0 times 10 to the -5. We'll make sure to square that. Then we have on the bottom the concentration of our chromate 2.0, our hydrogen 1.0 raised to the 14th. So that would still just be 1.0. And then we also had I2, that was 1.0 concentration. So all these values that I'm plugging in are right above here, 2 molar, 1 molar, 1 molar, and then the 1 to the -5th molar. All right, so we plug these in, and we should be able to find a Q equal to 5 times 10 to the -11. So we're almost there. Now we just have to plug in everything to our E cell equation. So I have my E naught cell, my standard conditions, 0.79 volts. Then I'm going to subtract this 0.0592 over 6, because this is the number of moles of electrons that have been transferred. And then I'm going to multiply that 0.592 divided by 6 by the log of my Q, which is 5 times 10 to the negative 11. All right, so you should be able to plug all this in, and we're going to see a small change in our voltage potential. So you should get overall a 0.89 potential for this cell in non-standard conditions.